thanks a lot for coming to this seminar. And okay, Sebastian already said many words about me. Therefore, I will then maybe just go to the presentation. And I hope you see the correct monitor. Sebastian, give me an okay. So here, okay, the colleague says everything.
Yes.
Okay. Okay, perfect. So then, yes, the idea is today to tell you and communicate about the progress in our CLASCO project, where we are using laser technology with the aim of reducing energy consumption in manufacturing processes compared to conventional technologies. And even better, if we can even get better functionalities and parts that compared to the state of the art. Just let me introduce my chair, the chair of laser-based manufacturing, that is here placed at the Technical University of Dresden in Germany. We are quite close to Prague and to Berlin. So we are working in every field of laser technology, particular laser micromachining, software functionalization, also dealing with classical methods like welding, cutting, hardening. And we are also developing photon-based metrology systems, which are very relevant to understand and see what we are doing in the best case in real time. I am at the same time responsible at Fraunhofer AWS for the business area development photonics. And we also have together, which is called the, I will go here, Center of Advanced Microphotonics, where we are then bringing the state of the art, what we learn from basic research, trying to also bring to technological applications and to industry. So together we are a big team. So you can see here some of the PhD students and also, of course, in cooperation with many colleagues at Fraunhofer AWS. So today we are going to talk about software functionalizations, and this is just to introduce you an idea, concept how surfaces can be functionalized, and in our case, and also in one of the topics of CLASCO, is trying to reach these special functionalities based on surface structuring technologies. And here the idea, as you have seen probably many presentations, is the focus of mimicking natural examples that have very well-defined surface geometries, also very well-defined surface chemistry. This is also very important to be considered. And we have the advantage of laser technology that can very precisely provide the energy at the position where we really want to process our material. So we have a unique tool to produce high precision features with nanometer resolution even, and also to enhance productivity, aiming to reach high throughputs of at least, it's our target in many cases of 1 or 2, 3 few square meters per minute. So just that you see some stuff that we are doing at the University of Dresden. I hope you can see the video running, but this is a system where, for example, we're texturing cylinders, and these cylinders then are implemented, for example, in roll-to-roll applications, where we are capable to transfer the texture from the sleeve, from the cylinder, to, for example, a polymer foil. And you see here, the structuring process can be long. I mean, it can take some time. In this case, for a 30 centimeters in diameter and 30 centimeters long slip, we need about 50 minutes, almost 1 hour. You see the change of the color due to the periodic structures. So very small, so light starts to be diffracted. And then we can put, for example, such cylinders in roll-to-roll equipment. And so we can also make different kind of motifs and so on. And then we just need to apply between these two cylinders that you see here. We have to apply temperature and pressure. And then you see here how the polymer foil is getting the structure from our texture slips. And one example here of a large area treated polymer, you can see there. So this is for applications, for instance, for antibacterial properties. You can have polymer surfaces that were with a very low adherence of bacteria. And the same structure is also ideal for enhancing the performance of organic solar cells or even perovskite-based solar cells. And we're talking about 10 to 30% improvements by using this technology. So this was just short introduction. So sorry, one more example. We are going to 3D processing, and we are working in other projects also bringing the implementation of robot systems for the first time, I would say, into micro patterning applications. That is possible because we are dealing with optical system shaping the laser beam, trying to get high precision and high resolution simultaneously, which is not almost so easy. So that was short introduction about our chair, what we are doing here in Dresden. And now this is the agenda for today for the CLASCO project. So I would like just to go to different aspects, of course, starting with our objectives, and then tell you our last results, at least what I can tell you regarding the parts that we're going to process, or we are processing actually, the laser-based surface treatments, the monitoring approaches, as well as artificial intelligence methods we're developing, and bring you a short conclusion. So I would like to start with this slide, thinking a little about the history and the motivation of this project. You know, things doesn't start from zero. So as Sebastian said in the introduction, we are working on laser micro machining or surface fossilization topics for a long time. And some years ago, I went to a beautiful application, maybe you know it, BOS Viewer. I recommend you to check it because you can make a very nice overview on the state of the art. And then, so you are analyzing, for example, in this case, we analyze more than 3,000 publications, and we start to see the interconnectivity between all these publications. Yeah? So you get then this optical image, let's say, that is connecting different topics. As you can see here, we also see the evolution in time, so from 2012 to 2018. And so at the very beginning, let's say, when you look laser micro machining or processing, you start to see some words like excitement lasers, because many applications started with mass projection technologies using the advantages of UV photons that are very strong. They have a lot of energy. They can functionalize surfaces very well. You see ablation, you see micron, you see laser machining. When you go a little further in time, so you start to see some technologies like interference lithography, also something about replication technologies, using molds, micron lens arrays as technology, ablation, and so on. And then going to 2016 and 2018, you start to see much more about application of picosecond, femtosecond laser sources. That, of course, with the evolution, let's say, of laser technology, today they are very a lot of use for surface fossilization approaches. And you also start to see then some applications. So weightability, super aerophobicity, these are things that there are quite a lot of publications in the field. And okay, so it seems, of course, we start from trying to understanding the interaction between laser radiation and materials, then looking for technologies that can make these special surfaces with high resolution, and then also the improvements of laser technology in order to bring this aspect. So this is a little what we are doing in CLASCO and what we have been doing in the last year. Just want to show you a slide I prepared for last LPM conference that was in San Sebastian, a very famous, let's say, conference in laser micro machining. I selected here just 3 projects. One where we were participants from Fraunhofer and TU Dresden, that was coordinated by BSH in Spain, in Zaragoza. It was called Laser for Fun. This was a doctoral network where mostly, let's say, We have 14 PhD students that were investigating how can we change surfaces to get special functions. So it was in 2015, the beginning, then continue, I mean, with this idea. So from what we learned there, we started with some application, let's say, projects. There was Lampas, Nikolai, that he is here in the room. He was participating in this project, for example. And here we were targeting to get functionalized surfaces at high throughput with high power picosecond laser sources. High power means 1.5 kilowatt, which is really a huge amount of energy for a pulse laser source with picosecond pulses. And CLASCO is like dedicated now on some of the topics, of course, of the previous projects, but we are also dealing with the new challenges that we could not solve in the past. And this in particular, for example, is related to the application and development of monitoring strategies and trying how to make laser technology much more efficient, faster, thinking on this all circular aspects related to climate neutrality. So therefore, that defines more or less the objective of the CLASCO project. So we are starting with laser-based technology to manufacture three-dimensional parts with additive manufacturing in comparison to CNC machining. Then we continue to the development of two laser technologies. First, to enhance the quality of the parts by laser polishing, and secondly, using laser structuring or interference patterning for getting special functions on these target parts. I will show you later. We continue with the development of inline monitoring process. We get a lot of information from our monitoring systems that we need to process, and the objective is to understand how can we get real-time information about the process to be much more efficient, to possible eliminate defect parts. What's at the end, we are saving energy and materials if that's the case. And then, okay, we go to the different demonstrators, and we have the last objective that is dedicated to analyzing or determining, calculating lower consumption of the sources energy, and also we are considering gender dimension in CLASCO. So if I have to put everything into a picture, this is, let's say, the idea of the project. So here you see on the left side, we start with powder bed laser fusion to create three-dimensional parts conducted by CATEC and the PUI synthesis. Then we go to laser polishing by SILAS, laser structuring, surfaction, and Theodresen. We have the monitoring systems that are based on camera systems and plasma sensors, NIT and Enlight Plasmo. So we get all this information, we generate our digital twin. All this is being done by SET Prime in our project. And then we have three different use cases in aeronautics, aerospace, and also in medicine. And finally, we have the sustainability analysis by ABC, circular, and of course, our dissemination exploitation activities that are being done mostly by DGM, that is organizing this event today. Also Steinbeis, Europa, Centrum, and CT Ingenieros. Let me show you something we wrote in the proposal. So here we have a nice table with one use case that we are developing. It's a clamp, so a generic component of payload bands for launchers. And we are analyzing gate to gate. So from gate to gate, materials that are necessary, the needed energy to create a part, also material waste, and considering the conventional manufacturing. So we need, of course, we start from a block of aluminum to make this part. We need like 440,000 kilojoules. That is calculated by using CNC machining. And we are taking, sorry, we start with not with 0.16 kilograms, we start with half a kilo of aluminum. So because we are same machining, we are taking out a lot of material, so we have a lot of aluminum that is not used. We have the coolant, we have the drilling tool. And the idea is to substitute all this by laser technology, so additive manufacturing. So there we can be already much more efficient by creating the three-dimensional part. So then you see the energy that we need for the fabrication of the part and the functionalization. So, and then also in this case, we almost do not have material waste, just the supports that are used in powder beam additive manufacturing method. So the savings are impressive. So we can save up to 50% of materials and auxiliary materials. We can save up to 75% of energy, and we almost, as I mentioned before, not have any waste. So this is the message, I mean, the mission in our project, trying to replace conventional manufacturing by advanced laser processes. And now I will go through the different work packages, showing you some advantages. So here we have some use case examples that include, in this case, the aerospace parts or applications, or lever, fitting the payload, clamp band. And so from going from the initial part by advanced designs using different algorithms. So with the aim, of course, of keeping also the mechanical performance of the parts. I mean, we still need to have some robustness of the parts. So here we can already save weight or reduce the weight by 13 to 25%. This is just the aerospace examples. There are also the medical examples that I'm not going to describe now into detail. But here we already see the potential of saving materials. And now, once we have these parts, we need to polish them, because laser-based powder bed function, you're starting with a powder. This powder attached to the melt pool that you are creating to the fabrication of your part. That means you have a very high roughness. So you always need an additional, let's say, polishing step. So we are going to do that, or we are doing that with laser polishing, not with machining, micro machining. And here you already see a picture of the actual state of the chamber from our CLASCO machine, the one I showed in one of the first slides. So we have here the module for laser polishing. Everything is into a gas chamber, because we are working with some materials like titanium, where oxidation is for sure a problem. So it's a 5-axis systems. And what you also see here now is already the integration of a monitoring system, a camera system, to control, to observe the laser polishing process in real time. And what is missing now is the second head, let's say, for surface functionalization that will be integrated quite soon. Let me show you some initial results regarding laser polishing of titanium alloys. So the roughness depends on the manufacturing angle that you are using in the additive manufacturing process. So you can see that the texture, they look a little different. And then, so from left to right, we are increasing the laser power up to about 540 watts, and you can see how the roughness of the parts strongly decreases. Yeah, we need to remember we have a waviness characteristic of the part. We had also our micro roughness, and we can strongly reduce both of them. Yeah? If we put some numbers to roughness values, and here we are considering the surface values and from the profile, so that the difference between SA and RA. So we look at the beginning here for the different manufacturing angles of 0, 30, 60, 90, 120 degrees. So we have roughness values over 20 micrometers. They're quite high roughness values. And then depending on the way that the parts were manufactured, we can see we can very strongly reduce the surface roughness, in this case, with increasing the laser power in the polishing process. So we are typically now reaching for this material alloy roughness values between 0.7 to 2.6 micrometers. So a very, very strong reduction. This can be also seen here in this scanning electron micrograph images. So a typical initial structure with some waviness that are related to the different tracks that are produced by doing the manufacturing process, the typical powder that is attached to the melt pulp, and then after the laser polishing process, we can observe very well the polished surface, and we even start to see then the different grains that are related to the microstructure of our material. That means now we have our material that is polished. That's a good news. Now the target is to get at some positions of the three-dimensional parts very special functions. And for that, we use interference structuring. And here we have now the company or function that is developing a new concept of optics that's called ellipsis. And basically, so we have an optical head with different optical elements that are used to do beam splitting, and then the beams are recombined, but they're recombined with a special shape, with special geometry. So as you can see here in the picture, we had very elongated spots. And within these spots, I can imagine you see all these lines. These are called and this is called an interference pattern. So we have a periodic variation of the laser energy. And what you see now with colors, these are the positions over the surface of our material that where we are bringing energy. That means we can ablate, we can remove, we can evaporate or melt the material just at this position. That means now we are moving our part following the direction, for example, of the lines, applying laser pulses, and in this way, then we can produce our periodic structure with, for example, high corrosion resistance, antibacterial properties, a higher biocompatibility, thinking on the implants, for example, low friction, and so on. So then these are camera, I didn't say that. These images were taken directly from the optical head with a CCD camera so that we can see our interference pattern. And then here there are some calculations. And remember, we have a machine that is going to process three-dimensional parts. And generally, when you are working with microprocessing technologies, you have the problem that you need high resolution. High resolution generally means that you have to focus your laser beam very strongly. And when you do that, what is called the depth of focus or focal depth is quite small. That means if you change a few hundred, even less, hundred of micrometers, the distance between your process head and your part, it could happen that you don't get your structure anymore, or that you have strong variations in the quality. That is what is outstanding in this new optical head, because what we observe here is the average intensity of the interference maxima, depending on the set position. So this is, again, the distance between the head and our surface. And you can see that we can keep an average peak intensity level of 80%, let's say, in a depth of almost 8 millimeters. In other words, that means that if your position from your optical head, your surface change 8 millimeters, you are going to get more or less the same results. Compared to a few tens or hundreds of micrometers, now we are talking about millimeters. This is a huge improvement thinking on 3D processing. So, okay, optical head is already working very well. Now, next steps here is to integrate the monitoring system directly into the optical head, and of course, to put this device into our final machine. So what can we do with the optical head? So I'm coming back to this result. You remember we have the polished surfaces that we make them using our laser based treatment. So now we took some of these samples that are polished and we started to produce our periodic structures. So And here you can observe some results. There's a lot of information, but just think in the first diagram. So we are looking the depth of our periodic structures. And what we are changing here is the overlap between our pulses. Remember, we're working with pulse lasers. That means we are pulsing, let's say, during the structuring process. And with enhancing the overlap, it means that a position of the material is irradiated many times. For example, 90% overlap means that we irradiate with 10 pulses, 95% is 20 pulses, 99% overlap means that we have 100 pulses coming to our surface at the same position. So now, of course, it's clear we are using more pulses if the overlap is higher, so the structure gets deeper. Here we have started to observe at very high overlaps some interesting results that we will come to that quite soon. And we can also make this diagram as function of the total energy that we use to irradiate the material. We observe here at the beginning also a similar trend, and then for very high cumulative fluencies, there is some randomness about the results. And where is this coming from? That in particular, when we are using very high overlap, for example, here 99.95%, so we start to destroy our periodic structure. We have a heat accumulation. We are bringing a lot of defects. This is, of course, something that we don't want to have. And in the case of overlaps, let's say up to 95%, maybe a little more, we can get very perfect periodic lines in this case. And these are the structures that at the end we need to create a spatial surface function. Just a little more information. Now we are looking here on the left side, regime 1, where we have very perfect periodic structures. We can not just see the depth information, but also how is the variability of the structure depth in the surface. And we see that here the error bars, this is important for us, are quite small. This is also talking about high quality structures. And in the regime 2 with very high overlaps, the error bars are huge. Of course, we are destroying the material a lot. So this variability is then very evident. So if we have to summarize this and put in some additional images, so if we use less energy, we create the periodic structures, but they are not so deep. We can see the initial topography, let's say, after the polishing process. In the middle, then we have some deeper structure with high quality, and if the energy is too high, then we start to have overmelting and we destroy our topography. In our proposal, we define that our target is to get an homogeneity of 90%. This is our target in the process to assure a high performance of our textures everywhere on the surface where we create our periodic structures. And you can see that for some conditions, we can reach that. This does not mean that there may be a structure with a higher homogeneity also will have a high performance. So at the end, it's a question of speed, of energy. This is going to be evaluated if we can make, for example, anti-corrosion property with 70% of homogeneity, but if we use 50% less energy, of course, that's what we are going to take. But this is, for us, a quality or a parameter determining the quality of our parts. So now let's go to the monitoring approaches. I will show you a few results regarding to this topic. So we observe already here mounted camera system, this from the company NIT. I didn't say the name of all the partners before, but you have seen the logos. So the people, the partners that are working specifically on the different work packages, let's say. So here we have the monitoring system that has been installed in axis, let's say, in the polishing module. So here we observe we have laser beam, there are some mirrors. Then the laser that's used for polishing is guided through an additional focal lens to our part. And we have here then the infrared camera that is collecting information directly from the process zone. And here we can estimate a temperature and then correlate this temperature or even fluctuations in the signal to quality parameters from the surfaces we're creating. This is something where we are working. The idea is not just that with this equipment we will be able to say, okay, now the temperature is, let's say it's just a number, 1000 Kelvin. We will be able to say, okay, now you are getting a roughness of 0.5 micrometers. This is the ultimate target. But okay, this is what we have now, camera installed into our machine. And this is a video that was taken during the process with changing, for example, the power of the laser. So you see in the central part of the image the spot that is collected. So here we are collecting then the different, let's say, intensity comes from the signal, and so this is working very well. We can even, if you, I don't know how fast is your internet connection, but you can see some fluctuations also in the temperature. I think these fluctuations are actually very, very interesting to get information about indirectly from the process from there, not just the absolute temperature. I think the fluctuations says a lot. This is something that we are going to investigate in the next part now of the project. So the second monitoring sensor is for the structuring process. Here we have Enlight Plasmo. So you can see here in one of our machines here, the TU Dresden. So we are now using the sensor out of the optical axis. So we are going also to put this in axis. But okay, we have some sensor that we have some lenses, some filters. We are looking to different wavelengths, ranges. We are looking the intensity of the signal we get. We also are looking into the fluctuations. We are sampling a very high frequency, much faster than our laser. Normally we are talking, or we are working on the 10, 20, 30 kilohertz, so we can really see each individual pulse coming to our material. And then, okay, we are analyzing the signal using Python, you know that software very well. And just to show you some insights, here was Marcelo, I think is here also in the meeting working. So what we observed, you know, in artificial intelligence, you don't really know what you are doing. Of course, if you know, it's better, but you can to identify some special features from your signals. And in our case, what we are looking now, so first approach, when we have a relative low variation of the intensity signal, in this case, we are like having very bad surface quality. And when we have, I mean, a higher variation in this case of the signal, we are getting very homogeneous structure. So this is could be a selection criteria for okay and no okay samples. We cannot say which is the depth, we cannot say which is the homogeneity, but at least it looks that we can see if we have overmelting or not. Other very interesting results are observed now when we take our signal from our sensor, we apply the so-called fast Fourier transform. This is a very well-known tool when you start to look to different frequencies. So this is a sample that was treated at 10 kilohertz. So of course, we are looking, we can see from the Fourier transformation, the pulse frequency or the frequency of our laser. And this is example of a okay sample. And for some reason that we don't know, we need to look when we have a no okay sample, there is a frequency shift. Why? We are not sure. We need to understand that, but this maybe is also a criteria to differentiate a homogeneous surface structure from a no homogeneous surface structure. If we put all this data, this is just taking the signals. Here is no artificial intelligence. We are just analyzing the raw signals. If you start to use artificial intelligence, of course, you get much more information. You know, you get these clusters that allow you to differentiate a different group of samples. Here it looks, yeah, for some parameters. let's say that we can identify the healthy data. Healthy data means in our case, these are the surfaces that have an acceptable homogeneity and surface quality. And then there are others that are quite easy to differentiate, so no case samples, and other that maybe is a little more complicated. So of course, here we are working much more with the focus on trying to get additional parameters that allow us to get a better identification of the structures that at the end we are processing. Tags for the future, not just to see if in real time, of course, if we are getting something good, something bad. The idea is to implement closed loop algorithms, so to control the process in real time, and even better, if during the process we can not just get information about the topography, but also to know about the property that we are creating. That means that from the signals we collect from our sensors, we can see, okay, the corrosion resistance for this part now is increased 80%, 90%, and that we can see and get such kind of information in real time. So then let me bring shortly to the conclusions of this first workshop, and then of course we have some time for questions. But I hope I could tell you how by using additive manufacturing we can reduce, for example, consumption of material by making advanced designs, keeping the mechanical performance as of course as is needed. That I could also show you first results on laser polishing technology. In this case, first on titanium parts that we can strongly reduce the surface roughness. Also, the advantages regarding the LIP technology, interference technology, that we already have an outstanding optical head with a depth of focus of several millimeters for the first time. This will make much easier the processing of three-dimensional parts, and also the first result on structuring on titanium. Of course, we have a lot of on aluminum, cannot show you everything. So it's working very, very well. The monitoring approaches that we have first results, it seems we can detect okay from no okay samples. So we are going further now to get more information about the process, and aiming, as I mentioned, at the end of the project to develop closed loop control systems for enhancing productivity, as well neglecting, let's say, defect parts. So making a high efficient laser-based manufacturing and functionalization process. Okay, that was the last slide. So I thank again you for coming to the talk. And now let's say we have time for some questions.
Thank you very much, Andres, for this very interesting presentation. Are there any questions? Just maybe raise your hand, then you can do that in a structured way. Then let me start with the first question. What are the next steps for the CLASCO project?
Yeah, you know, like in, let's say, European projects, in case of CLASCO, we were, I think, very clever in trying to assemble all parts from all components that we need in the machine quite, I mean, not at the very end of the project, but in an accepted time scale, so that we can start to prove everything together. So I think that is the most important task for the next month, so that we can start to learn about the machine, because for sure we will be confronted with a lot of problems that we are not expecting, like always. So we are starting at low tier L level. So when you design a technology, you don't know everything that's going to happen. So But to get this information and this experience, so it's very important that we can assemble our machine, the first version, let's say, of the machine as soon as possible.
Thank you. And there is also another question from Mr. Wagenblast. Please.
Can you hear me now?
Yes.
Yes, yes.
Hello, Mr. Lasagni. Yeah, thank you for the presentation. I'm from Trumpf Additive Manufacturing. Therefore, I would be especially interested in the first part of your talk where you showed the your laser polishing arrangement. I saw that you have a multi-axis system there. Are there plans during the project to do some surface treatment for the demonstrators that you have shown?
Yes, of course. The idea is so we take the three-dimensional part. We define the areas that are critical to be polished first, and then we define the areas that have to be functionalized. And of course, we are working in 5 different use cases. So at the end of the project, we will have 5 real demonstrators where we are going to hopefully be able to improve the quality of the parts and functionalize them. Yes.
Right, thank you. So I would be very interested in seeing these results later on in the project.
Yeah, I hope this, as I mentioned, now once we have the machine running, that we are mounting now the different parts, that we will start to gain experience in 3D processing, and then to have these demonstrators, the first version at least, ready quite soon. By the way, Lampa's project, Philip, was with Trumpf. The 1.5 kilowatt laser was from you. Any other question? Comment? Suggestion? We are happy if you can guide us a little. Eduardo, I see you now. Hi. No comments, questions?
Hello.
Hello.
My name is Mansoor Ahmed, and I'm working in DCU, Dublin City University. And previously, I had opportunity to work with laser polishing of the additively manufactured samples, especially titanium samples. So we had worked with a company like aerospace companies. But the problem was they wanted to polish the additively manufactured sample, which is hollow shape samples, like internal hollow. So how do we polish the internal surface? So that's the question, if any. So what will be the arrangement?
As clear as a limitation. So the free design of the parts includes trying to make, let's say, trying to help the laser to reach the surfaces as much as possible in order that we can polish as much as we can from the part. Yeah? So the new design of the different demonstrators includes that target. In case of the, the parts for aerospace are normally aluminum alloys in our case. So there are some areas that are critical, and so we need to see how to make that better. In case of the titanium parts, we are working with implants, and they are quite easy from the geometry. The geometry is three-dimensional, of course, but there are not any difficult, let's say, areas to be reached by the laser. But you are coming to a very good point. This is a problem. Yeah. So and this is a limitation at the end of the technology we are developing.
Okay, thank you very much.
You're welcome.
Any more questions?
Yes.
Eduardo, yes.
Sorry. Thank you for your presentation, Andres. It was very nice. You work with what kind of materials? Titanium, aluminum?
Yeah, in this project we are focused on titanium and aluminum alloys because
Yes.
they are the end related to the use cases, so the demonstrators that we want to treat. In previous projects, we also have some experience with steels and so on. So,
Okay.
I mean, okay, it's very important when you are putting energy, let's say, into a metal, also to understand oxidation processes and many things that maybe they are of huge disadvantage on the performance of your parts. Therefore, you have seen maybe that in this chamber where we are doing the laser treatments, both laser treatments, we can control the atmosphere using inlet gases and so on. Yeah.
Okay. Thank you.
Okay.
And there is another question, Mr. Krenich.
Hi, my name is Tim Grenning from Oak Ridge National Lab here in the United States. My question is regarding scalability. So when you
regarding, can you
this,
repeat, please?
Yes, scalability.
Scalability.
Like how do you intend to scale the parts you're making, and how fast would that be?
Okay, so in both technologies, we're using kind of elongated laser beams. Yeah. Okay, laser polishing not always. Yeah. But this is clearly an objective always. I mean, if the process is not fast enough, it makes no sense. Let's go to the point. Yeah. So it doesn't. If you make 1 centimeter square in 6 hours, this makes no sense. So the concept, for example, regarding the optical head for laser structuring, we already could reach throughputs of 1 square meter per minute. It depends, of course, on the laser source you have. So you need some power. Pasteurization also is important, but the way that we are shaping the laser beams allows such kind of high throughputs. That means that in a few seconds or maybe in a few minutes, our demonstrators will be processed. In case of the use cases related to aerospace, you are not doing 1 million parts per year, you are doing few parts, so that time is not so critical. Yeah? But in the implants, okay, there are also not million parts implants per year, but there you have to be a little faster. So this is, of course, something that is also to be calculated, let's say, in CLASCO. But from the numbers where we started the elaboration, preparation of our proposal, we can see that the technology can be productive and cost efficient. Yeah? So the substitution of the so many other process steps that we are doing, even in some cases, we get lower costs than the conventional manufacturing. At the end of the day, we will see. For this case, it works. For this, maybe not so good. Yeah, but it's part of our evaluation in the project. Yeah.
So far, it has been used only for laser powder bed, but is it also potentially feasible to be used for DED or for other projects? And I understand that your parts are relatively small, but when I'm thinking of the industry I'm working in, where for larger pieces or for larger parts, of course, laser powder bed has limitations regarding the size of the bed. And if you think of other methods that would be of interest, is there some thought process going in that direction? Sorry for the second question.
Yeah, I understand your point. So here we have some limitation in our chamber. So that means that is limiting also the size of the parts that we can treat. But when we are thinking on really, really large parts, maybe you remember the beginner showed this video with the robot arm. Yeah. So that concept was actually inspired by the functionalization of forming tools. You know, they are huge. They weigh some 1,000 of kilograms. you cannot move the part. There's no chance. You have to move, let's say, your laser on the part. So the optic for surface functionalization is compatible. The laser polishing process could be also be compatible. So there are ways to address larger parts and other, let's say, objectives. Yeah. So
good to hear. Thank you.
Thanks for the question.
Any more questions? That seems not the case. Just to comment, if you are interested in updates from the CLASCO project, we would be happy when you follow us on LinkedIn, Facebook, X, or soon also YouTube, and of course on our website.
Yeah, thanks everybody for coming. So it was nice. Thanks for the questions. And yeah, hope to see you soon in another event around the world. Yeah. So thanks again. Bye-bye.